Hello, in this final video on section 7.1, we are going to be continuing our discussion on exponential functions by talking about interest formulas. In past lessons, you may have already covered simple interest formulas, and you may even have already covered compound interest formulas, but that's where we're going to start today. So a compound interest scenario is a case where you are receiving your interest more than one time a year. So, for example, this P would be the principal or your starting amount. We multiply it by 1 because after some time has passed, you still have that 100% of your starting amount. But we are also going to be adding on a certain percentage for your interest. The R represents your rate as a decimal. N represents the number of times that your interest is going to be compounded. And our T represents the time that has passed. If time is in months, then my number of time compounded needs to be months. Generally, we talk about time in years, and our number of times that we compound our interest will be given to us in years. But the units on N and T both need to match. We're going to go ahead and talk about what happens to our amount in our bank if we are compounding our interest at different time intervals throughout the year. So in this scenario, I've got $1,000 and I'm investing it at 10%. We're only going to look at what happens after a single year, and we'll complete the table using the formula above. So if we are compounding annually, then in the course of a year, I'm going to have just one deposit of interest into my account. The formula then is going to be the amount in my bank account after 1 year would be equal to $1,000, that's my starting amount, times 1 plus 10%, so 0.10, over 1. And then my exponent, I'm compounding one time a year, and the time that's passing is 1 year. Simplifying and multiplying all of this out, I see that I will have $1,100 in my bank account at the end of the year. Quarterly means that we are going to have our interest deposited every quarter or 4 times in 1 year. So that means that my N value will be 4 because we are looking at years. I'd like for you to go ahead and take a moment to pause the video and complete this chart on your own. So I'm going to look at the amount after 1 year still. The amount is still, the initial principal is still 1,000. I have 1 plus, my interest rate is still 10%, so 0.10 over, and my N, or the number of times we're compounding, is 4. And I have N is 1 multiplied by my time T, which is 1. Simplifying this, $1,103 and approximately 81 cents. So we can see that even though we did not change the initial amount of money we deposited, we did not change the rate that we are earning, we only changed how many times they are going to be breaking up our annual interest. So they give us a little bit in the first quarter, a little bit in the second quarter, a little bit in the third quarter, and the remaining of the 10% in the fourth quarter. If they break it up into 4 payments, then we earn an extra $3 as opposed to if they give us our interest all at one time. For monthly, we're going to have 12 payments, and daily, we're going to assume that we have 365 payments, and it is not a leap year. For monthly, when I plug in and simplify, I see that we're about at $1,104.71, 365 payments. We are at about $1,105.16. So the more intervals that they break up our interest into, the more money that we are going to earn on our initial investment. And just to recap, we have our compound interest formula here and our variables defined below. Now this is an exponential function, and we can write it as such, with t being our variable, by saying I have p multiplied by, and I'm going to put my base in brackets, 1 plus r over n to the power of n. These are all values that we would plug in. R is not a variable, n is not a variable. Those are numbers that we are given depending on the scenario that we're looking at. P is also not a variable. We would plug in a value for P, our principal. But T is a variable. It changes depending on the amount of time that you are looking at. So we really have two variables in this scenario. We have A, which is the amount in our account, and it depends on T, which is our time. So we can look at this as an exponential function. A of T equals A times B to the power of T, where A is my principal and B, my growth factor, can be found by looking at that base of T. Go ahead and take a moment to pause the video and try example 718 on your own. I've got an account balance after time t, and here we're looking at a time of 10 years. And that's going to be equal to my principal, which is 3,000, multiplied by 1 plus my rate, which is 0.03, divided by the number of times that we're compounding. Here we're compounding quarterly, which means they're going to break up that 3% into 4 payments. And I will be raising that to 4, my n, multiplied by 10, my time. Simplifying, I find that the amount in my account after 10 years is $4,045 and approximately 5 cents. All right, again, go ahead and take a moment to pause the video and try example 719 on your own. Now here they want the account to grow to a final amount of 40,000. So the amount after time t is P, the principal, multiplied by 1 plus r over n to the power of n times t. Here they want this final amount to be 40,000. And the time is going to take 18 years. So I know that I'm going to have an exponent of n multiplied by 18. She believes the account will earn 6% compounded semi-annually. So I know that my R is going to be 6%, 0.06. Semi-annually means 2 times a year. So in my exponent, I have 2 times 18. And what we want to know is how much we need to invest now. So what's our principal? So I'm going to go ahead and simplify that right-hand side as far as I can, and then I will divide to solve for P. When I simplify, I have P times 2.89. I'll go ahead and go out a couple more decimal places just to be a little bit more accurate. And then to solve for P, I divide. And completing that division, I find that I get $13,801.30 for my initial investment. So she's going to need to deposit approximately $13,801.30 into the account in order to have a total value of $40,000 in her account after those 18 years. What we're going to look at now is what happens as we increase our value of n, so in this case 2, infinitely. So on this chart, what we have here is the value of n increasing from 1 to 2 to 4 to 12 to 365. So we went from annually to semi-annually to quarterly to monthly to daily. I now have 8,760 payments, 525,600 payments, and approximately 3 million payments every year. So what we're looking at is the time in between payments is decreasing. If I go from once a year to 4 times a year, the time in between my payments is decreasing. Instead of getting paid once a year, I'm now getting paid every 3 months. Going from 1 payment a year to 12 payments a year, instead of getting paid once a year, now I'm getting paid every month. So the time in between my payments is decreasing, meaning we are getting more frequent payments throughout our year. So as that N increases, what happens to the value in our account if we start with just $1 is that the value in our account is going to continue to increase, but notice that it starts to approach a number that doesn't seem to change very much. Here we see the 2.71. Here we still see that 2.71, now 8. Here we still see that 2.718. Now I have a 2, 2.71, 8, 2, 8. So we start to approach a particular number. And the number that we approach as that N value gets bigger and bigger and bigger is what we call E. We approximate E to be about 2.71. So just like pi, E has a constant value and it is not considered a variable. So the values are approaching a limit as N increases without bound. In fact, as N gets larger, this number approaches a number so frequently used in math that it has its own name, the number E. And here is an approximation out to more decimal places than I gave you on my last slide. So continuous growth and decay, what this means is that our time between intervals is almost indistinguishable. We are getting paid continuously, and there are no distinct points at which we are earning our interest. So not yearly, not semi-annually, not quarterly, or so on. We are getting paid continuously. A is still our initial value. Before we called it P. T is still our time. R is our growth rate. So here in my exponent, I have that percent. If R is a positive number, then it does represent growth. And if R is a negative number, then it does represent decay. Now you may have seen this before where A is replaced with a P, and we often refer to this formula as PERT. So go ahead, take a moment, pause the video, and try examples 7.1.10 and 7.1.11 on your own. Here I see that we are compounding continuously, so I want to look at the amount in my account after time t using my continuous formula. The time t we're just looking at is 1 year. My principal is $1,000. I'm multiplying by E because this is continuous growth. And we are earning an interest rate of 10% per year. Your calculator does have an E button where you can compute the approximate value of this by using that button, and I'm going to go ahead and do that now. In doing so, I get a value of approximately $1,105.17. Example 2, we are talking about decay of 17.3% per day, which means we're going to have a negative R for a continuous growth or decay scenario. We want to know how much we will have left after 3 days, so the amount after 3 days. Our interest rate is in days, so since our units match, we're okay to proceed. I start with 100 milligrams. We are decaying continuously, so I have E to the power of negative 0.173, or 17.3% as a decimal, and we're talking about a time of 3 days. So using my calculator to simplify, I see that we will have approximately 59.51 milligrams of radon remaining after those 3 days. That brings us to the end of our video and the end of section 7.1. Thanks so much for watching and have a great day.